Okay, well, it's my pleasure to introduce our speaker for today, Sandy Zabell. Sandy has many connections with Rutgers, many connections with some of us personally. He has been a speaker already in our Foundations of Seminar series, talking about Turing and his work on code breaking in World War II, Bayesian work on code breaking. Today, he's going to, well, I should say a few words about his distinction as a mathematician and a statistician. He's in those two departments at Northwestern, but he's also one of our leading historians of probability. He and I are of the same generation. We were students about the same time with the same teachers. And we are the generation that really, I think we can brag that we expanded the history of history as a generation. And maybe some people a little bit older than us really expanded knowledge about the history of probability and statistics. So it's a real pleasure to have someone with those interests talking. And today he's going to talk about, he's going to pull together the history and philosophy and probability theory by talking about the setting and what Carnap did, Rudolph Carnap did in the philosophy of probability. So take it away, Sandy. Thank you for being here.
Hey, thank you. So first of all, let me do share screen. Share. And then let me go to slides and go to full screen. So everybody can see the slides, yes?
Yes.
Okay, so first of all, it's a great pleasure to be here. My current research is in a couple of areas, and I've spoken here before about a sort of very different area, which is the use of cryptography and Alan Turing during World War II. An subject of great interest, and to me, because Bayesian statistics was an important part of the Bletchley Park attack on German encryption systems during World War II. But today, excuse me, I thought I'd talk about something different, which is I've also had an interest in Carnap for quite some time. And recently I was asked to write a chapter in the book interpreting Carnap. And so I thought I would combine the two activities. So for people who are interested.
Put a bandage, bend your arm up, and then I'll bandage it. Oh.
Sorry?
Sorry, no worries.
Yeah. So for people who are interested in the talk, besides the slides, probably within the month, there'll be a formal paper that will correspond to this. Okay, so the outline, so introduction, which I just gave, and I actually have a more extended introduction, but I'm actually going to have this post talk, so to speak. Take 5 minutes out just to say why Rutgers actually played an important role in my interest and philosophical viewpoints. I'll talk briefly about Carnap's life because I think that that's of some interest in terms of why he got interested in probability. So I'll very briefly though, I'll then so these are not equally sized segments. I'll talk a little bit about his work, sort of just an overview of what he did in probability and inductive inference. And then one part of the talk, which was going to be fairly small, but then sort of just expanded as I was preparing it, was some historical discussion of the dual nature of probability. Because if I had to guess, for people who are not Carnap scholars or heavily invested in the foundations of probability and statistics, if you mentioned Carnap's name and said, well, what did he do in probability? I think a lot of people would at least know about this idea of probability 1 and probability 2, the fact that he thought it was important to distinguish these two senses. So I'll talk a bit about that. And then I'm going to give some case studies. So the thesis, as I mentioned in this, in the abstract, is that Carnap started off in a sort of he had been involved in logic, obviously, And so he had a very logic-based approach initially in his logical foundations of probability. But the thesis is, if you really want to understand him, you should, like to a very great extent he actually did, shift over and view things in the more in the viewpoint of modern mathematical probability. And so I'll give 3 case studies of issues that arose that were discussed after he got into the field. One being total evidence, another something called instantial relevance, another called universal generalizations. I could actually advance other instances as well, but that'll probably be plenty for an hour. And the point in each case is that these were subject to a lot of discussion and so on. But if you look at things the right way, actually they're, I claim, so it's grounds for debate if you want, discussion, that actually there's very little mystery to any of these. But you actually have to start looking at them within the probability context. And then conclusions, I think maybe I'll leave for the discussion. Okay, so to move on, I think it's always useful when you're talking about someone to have some general idea of his life. So 1891 to 1970, he was born in Germany, Wuppertal. And then he got his bachelor's degree at the University of Vienna, but the World War I intervened. And then he went back after the war and got his PhD. And now the 1921 is interesting because originally he wrote a thesis in 1920, which was turned down. Why? Well, it was a melding of, it was basically philosophy of physics. And the physics guys said, what is this? This is just like philosophy, go away. And the philosophy people said, what is this? This is like mathematics and physics, go away. So he wrote a second degree that was more or less purely philosophical in nature. And he was given his degree. And I'm saying PhD, but of course, if you get into the German system, it's a little more complicated, right? They had basically 2 doctoral degrees and the name of the degree depended, but I'm just using PhD as a stand-in for first doctoral degree. Okay, so 1921, he gets his degree, although really he wrote his thesis in 1920. And then from 1926 to 1931, he was an instructor in philosophy at the University of Vienna. So you have the Vienna Circle, more Schlick and so on. So that was a very natural place for him to go. And then this is, of course, the first typo of the slides is it's 1931 to 35. He moved to Prague where he had a chair in natural science. Okay, but things were starting to get a little dicey in Europe at that point. And so he had the good sense to leave in 1936, and he left for the US and became a professor at the University of Chicago. He had a productive period there, but he wasn't terribly happy because there weren't that many people who were really had the same sort of interests in philosophy. He spent a very productive 2 years at the Institute for Advanced Study, and that's where he met some of his collaborators like John Kemeny. And then he moved to UCLA in 1954, which is where he remained for the rest of his life, and he died in Santa Monica after a brief illness. So that's his life in short. Okay. Now, if we look at his writing, I couldn't resist a digression here, which isn't, I don't know, actually, maybe someone does. If there's been, so it's well known, but I don't know if someone's actually written an article about, so I attended several years ago a conference at Oberwolfach on the impact of emigration on mathematics immediately before, during, and after World War II. And I wonder if anyone has written anything, at least a paper length, talking about the emigration of philosophers out of Germany in particular, but more generally Europe, in the years leading up to the First World War. And so I've listed the names of philosophers, probably all of whom you've heard of. So first and foremost is Richard von Mises, very interesting because he was responsible for the frequency theory of probability. But one of the reasons I have very high respect for him is that he left Germany for Turkey, Istanbul, in 1933. And the reason that's interesting is, although the Nazis came to power in 1933 and they passed a legislation to expel Jews from the universities, there was an exemption for people who had done service during World War I. And Mises fell into that category. So he actually wasn't included in the first round of dismissals, and he could have stuck around. But he was a very smart guy, and he knew time to leave. So he immediately left, even before he faced dismissal, and was in Turkey until his contract expired in 1939. And then he decided Europe in general was probably not a great place to be. So he left for the US, which is where he remained the rest of his life. Another person as part of this diaspora was Reichenbach, a German colleague, who left for Istanbul as well. Although in Reichenbach's case, it was a bit easier or more clear cut, because he had leftist politics, and he knew he was going to be in trouble under a Nazi regime. So it seemed advisable to leave as quickly as possible. Ernst Cassirer was actually Jewish, so there was no question whatever. So he left for first Oxford, and then ultimately the US. Karl Hempel left for Belgium in 1935. And then you can see that these people tended to go for the most part to the US. Kurt Grilling is a sad story, because he left in 1937 for Belgium, but he stuck around. And so Belgium was, of course, occupied by the Germans in 1940. And so in 1942, Grilling and his wife were arrested, carted off to Auschwitz, where they were killed gassed within either the same day they arrived or very shortly thereafter. Weizmann left for the UK in 1937. Now, so Weizmann was Austrian, and there are others too. So Tarski was Polish, but he obviously knew time to leave. And Kurt Gödel, again, although super smart in some ways, sort of stuck until the very last minute. And so he was able to get to the US via a fairly circuitous route. So you can see that even though he was in Prague, not Germany, it was pretty clear to Carnap by the end of 1935 it was time to leave. So some people, it's very hard to break off ties with the country or you were born in and so on, but some people recognize things, and some people were more reluctant in some cases. It cost them their lives. Okay, so now here are some intellectual highlights in Carnap's career. He wrote many books, he wrote many papers, but one of the reasons I wanted to lay this out. So initially he had these two famous books, Logical Construction of the World, Logical Syntax. And then after he moved to the United States, he published two books, Harvard University Press, Introduction to Semantics, Formalization of Logic. And then he wrote a first draft in 1943 of a book, Meaning and Necessity, which was published in 1947. So my point though here is it's very interesting if you look, so he worked in logic, philosophy of science, logical positivism, but then there was this seismic change. And what it occurs to me I should have done over here was in 1945, he wrote two papers. One was on the dual sense of probability, another was on inductive inference. And so he became interested in the early 40s in probability and inductive reasoning, which is something really which was peripheral to his work prior previously in the 30s and 20s. But then partly because he was at Harvard at one point and met Mises, he became interested in probability and inductive inference. So he started publishing papers on them, and really most of his work from that point on, certainly from 1950. So in 1950, he had his famous The Logical Foundations of Probability. 1952, he wrote a monograph. See, originally, Logical Foundations of Probability was supposed to be a 2-volume work. And he was going to go into, and he already realized but when he was finishing the book, but before it was published, that his initial system, which he called C*, wasn't really adequate. And he was thinking about a 2-dimensional system. And then he said, there's going to be a volume 2 where I'll talk about this more complicated system. But then when he started working on that, it became sufficiently complicated that he realized I'm just going to publish this as a monograph. And now it's sort of the Shope volume that came out in 1963 is sort of fascinating because he has an intellectual autobiography, comments, responses. So it's a great book to get a sense of where he was in the 60s. And then, but the point was after the Continuum, he had this picture that I'm going to write books and so on. But by the 1960 or so, what he decided instead is he had a research program. He was very fortunate in his collaborators. One of them was Kemeny, John Kemeny, who became president of Dartmouth later. Another one was Dick Jeffrey. And so now, after he died, something called Studies in Inductive Logic and Probability, co-authored with Jeffrey, but it had been finished essentially by the time of his death. And then further material was published posthumously, both articles by Carnap and also by some of his co-authors in 1980. In fact, I was visiting, this is part of this connection with Rutgers. I was visiting Rutgers in 1978-79, and I remember I was down in Princeton talking to Dick Jeffrey when the proofs to volume 2 came out, and he scurried off. So, my point is that there was this seismic shift, and so if you say really his postdoctoral careers from roughly 1920 to 1970, 50 years, the first 25 years are in logic and some related fields, logical positivism, philosophy, science, and then the second half is primarily probability and inductive inference. And so this was really sort of a midlife change for him. And then if we look at what are here are some major works. So as I mentioned, there were the 2 concepts of probability and on inductive logic. So these were 2 papers, and then he had another paper on but the point is in 1945, in a certain sense, he has an outline of what was in the logical foundations of probability. And then, whoops, sorry, this mouse is a little sensitive. And then he has something, the application of inductive logic, where he talks about the principle of total evidence, then logical foundations, the continuum of inductive methods. Then he continued to hone his system, and some technical developments were included. So Stegmuller published a German translation of a lot of what was in the book and monograph, but there's also an appendix at the end, which gives some important technical advances. He wrote a book in 1962 that showed that he hadn't completely renounced his sort of old ways of thinking about things. But then posthumously, there was the basic system of inductive logic, part 1. That's in the first Jeffrey volume. Some notes, posthumous notes were published on probability and induction. 2 essays on entropy, edited by Abner Shimoni. And then in the second Jeffrey volume, basic system of inductive logic, part 2. So if you want to know what his final views were in terms of his system, these 2 are the basic sources to turn to. Okay. Okay, so now moving on. So the first topic I'm going to talk about at some length is, as I said, people, if you think about him, you think about the dual nature of probability. So he insisted on the distinction between what he called probability sub 1, which was degree of belief, epistemic, versus probability 2, which was aleatory or physical. But as Ian Hacking in his wonderful book, The Emergence of Probability, noted, the duality of probability has long been known to philosophers. The present generation may have learned it from Carnap's weighty tome, Logical Foundations. So one thing to remember about logical foundations is it's really sort of a work of synthesis. I mean, this was a field that Carnap died into. There's an enormous, very large bibliography at the end, which in part can be thought of as picking up. So Keynes's 1921 treatise on probability has a very extensive bibliography at the back, not all of which Keynes read. He has a comment at the beginning saying, there are many books here, but more than it would be good for any one person to read. But then if you combine that with the bibliography to Carnap's logical foundations, that sort of updates you in 1950. And then if you look at the bibliography in Hacking's 1975 book, that'll update you in 1975. And after 1975, it's just hopeless, right? There's just so much that's come out. But the point is that you should think of now what Carnap brought to the table was a way of trying to think about things clearly. But it was a work of synthesis, and he obviously knew he wasn't starting from scratch. And so he's not responsible for this dual nature of probability, although he puts it in this frame of explication, the explicandum and the explicatum. But the notion itself, he had predecessors in Cournot and Poisson and Ramsey, and I'll talk about the first two. So here's now, for people who find themselves intrigued by Cournot, you have a wonderful resource at Rutgers, namely Glenn, who's also very interested and has written a very nice working paper discussing Cournot. So Cournot, 1801 to 1877. So he's in the post-Laplace generation, if you like, the generation immediately after Laplace. He studied first at the École Normale Supérieure and then at the Sorbonne. So two of the outstanding French universities, not just now, but back then. And then he had a pretty very distinguished career. He was a professor, but also rector at the University of Grenoble and then Dijon. And he's perhaps best known as a pioneer in mathematical economics. But he also wrote a wonderful book called The Exposition of the Theory of Chances and Probabilities. There is an English translation by Oscar Scheinin, although, if French is not bad, it's quite readable. And references are, there's a scholarly edition brought out by Bernard Roux, outstanding historian of probability in France, a younger colleague, Thierry Martin, who's written about Cournot, and Glenn Schaefer himself. Now, so if you had to assign priority, who is the first person to come up with this clear distinction that Carnap made, I'd say I'd nominate Cournot, even though, as Steve Stigler once warned me a long time ago, it's always very dangerous to say so-and-so was the first person to do something, because someone will always come out of the woodwork afterwards and say, no, you overlooked this obscure person who 30 years earlier did thus and such. But you'll see in a minute why I think Cournot is permitted some precedence here. So the preface to Cournot's book says, and now, by the way, I've taken slight liberties in the translation. For example, I'm omitting the ellipses and so on. But he says, the part of my work to which I attach the most value is that which aims to make clear the philosophical value of the ideas of chance, hazard, probability. Now, there are a lot of really interesting things in this book. There's arguably the first clear discussion of confidence intervals. But Cournot himself says, in my opinion, the thing that's most important is the philosophical clarifications. That's what I think is the most important thing I did. And then he says the explications, and that's the actual French. So remember, Carnap says, develops this notion of explication, right? You have the imprecise concept, and an explication is either a precise or more precise version of that. And so Cournot says the explications I have given about the double meaning of the word probability, which sometimes refers to a certain measure of a knowledge, probability 1, and sometimes a measure of the possibility of things, independently of the knowledge we have, which is really basically Carnap's probability 2. And then, like Carnap, so Carnap, why was Carnap engaged in this? He thought there's all this this was part of a more general philosophical viewpoint, of course, but he thought there's all this controversy and confusion and discussion because people just aren't getting clear about what the concepts are. So of course they're arguing. And so Cournot says, similarly, he says, these explications seem to me suitable for resolving the difficulties, which have up to now rendered suspect to bon esprit. Maybe someone in the discussion can come up with a better word good, best minds maybe, or good minds. It's a little hard to, there's no really good English translation, but to the rendered suspect to the bon esprit, the whole theory of mathematical probability, mathematical. And so after Laplace died, there were attacks on a lot of the Laplacian edifice. And Cournot saying, well, a lot of this is just because people, a lot of the argument is because everything is so fuzzy. And then he says, one will find their definitions, which and ideas which I believe to be new, or at least they've never been clearly perceived. Now, it seems to me, for my little modest claim, that we really, if we want to say, when's the first time is this Carnapian kind of distinction made, this is my justification for that, because as Glenn will tell you, I mean, Cournot was a very widely read, cultured person. He was very knowledgeable. And if he's saying, I think what I'm talking about is new or not clearly perceived, I mean, he's coming from a very considerable body of literature. If he didn't know about these things, almost nobody did, if nobody. It's very hard to argue on the basis of this that there was anything out there that could be comparable in clarity and scope. Now, there is a little competitor. There is one other person. There's Poisson, who's a somewhat younger, well, earlier generation, so the same generation as Laplace. And so he too very excellently connected. He studied at the École Polytechnique. He was then a professor there, and he's obviously a superstar. His advisors were Lagrange and Laplace. His students included Charles and Liouville, and he's well known for his contributions both in mathematics and physics. But for us, the interest is a book he wrote towards the very end of his life, researches on probability of judgments and criminal matters and matters civil. So one of the things that both Condorcet and Laplace had done Laplace, more in passing, was discussing the applications of probability in legal matters. Sort of what's the chance that a jury will get something right, that kind of thing. And so this was a book that Laplace wrote on that subject. And now, what he says is closely related, but I claim it's different. So he says, in ordinary language, the words chance and probability are almost synonymous. Most often, we will use one and the other interchangeably. So whereas Carnap was saying, we have this one word probability, and the problem is there are two different senses that people attach to this one word. And we have to deconflict that by really sort of, I'll call it probability one, probability two. Poisson is saying something different, which is saying there are these two words and people are using them in the same way. So it's, rather than 1 to 2, it's 2 to 1. But what he's indicating is that as technical device, he's saying when it's necessary to make a difference between their meanings, so he's saying, yes, people do actually, there are different things going on, will relate in this work. The word chance relates to the events in themselves and independently of the knowledge we have of them, very close to Poisson, to Cournot. And the word probability will retain its previous definition in this book, namely degree of belief. So he summarizes an event will have by its nature a greater or lesser chance, known or unknown, and its probability will be relative to our knowledge as far as it's concerned. So very close to what Cournot had in mind. Now, in Cournot's book, he has a very funny letter at the end of his preface. And so in 1836, he found out that Poisson was writing this book, and he was also himself in the process of working on this. So he sent a letter to Poisson describing what he was doing, and Poisson sent him a letter back saying, oh, by the way, so here's his introduction. Before we see the letter itself, here's the introduction to the letter. He says, I will be forgiven for transcribing here, much less to preserve my rights to the priority of certain ideas, than as a testimony to the memory of someone who will be always precious to me. So he's sort of saying, actually, I'm doing this because Poisson was, a very precious person to me, and much less so. But he doesn't say not at all, right? He's not saying that at all, but he's saying, you know, he's conceding he's also trying to preserve his rights to priority of ideas. And this is the opinions of a famous man. And so he says, the letter that Monsieur Poisson wrote to me in answer to another, where I submitted to him the outline of the book, which I published at the moment. So what was this letter that he, from Poisson? Poisson, 1836. So this is a year before Poisson's book came out. He says, sir, it will be with great pleasure that I will read the work that you propose to publish on the Doctrine of Chances. It's a very funny letter. He says, the one I'm currently finishing will not be an obstacle there. And I'll leave plenty of room for a more complete book, don't worry. Okay, but he's currently finishing it, right? So he says, I've put the same difference between the words chance and probability as you. And I've insisted on the same difference. Now, as I'd mentioned, Poisson was sympathetic to this program that kind of same Laplace had of trying to come up with an analysis of legal matters. And he says, and Carnap was much more skeptical. And so he says, I'll compare it to mine when I review and settle this part of my work. And then he concludes, he says, that's all I have to do and copy everything to be able to start printing. In other words, my book's finished. You didn't scoop me. You contacted me when the book's essentially finished. I just have to do a few things. There are also a few problems I might work out and put in the final chapter. But basically, the book is done. And he says, finally, you'll see that I don't reject this part of human knowledge, metaphysical consideration. So again, that's this disagreement they'll have. And then he somewhat pompously finishes up. It is from the council, that is the Conseil d'Etat, which was a leading important French administrative body. It is from the council I'm writing to you. And as the floor is about to be given to me, I cannot write a longer letter. Goodbye. And then there's a flowery, typical flowery French closing, which I give in the original French, except, Monsieur, the assurance of my attachment, my complete devotion, Poisson. So, if you like, Poisson and Carnap clearly have this distinction in mind. And it's very difficult to come, I mean, there are some things that Bernoulli says and some things that Condorcet say, but in terms of this, insisting that there's two very clear subjects and so on, this is, goes back to that. Another thing, by the way, that Carnap introduces is he introduces the term subjective and objective. In the modern sense, these are terms that Kant used, and Carnap, is very familiar with Kant, and so he introduces subjective and objective as ways of distinguishing between the two types of probability, whereas for Carnap, they have a different meaning. This use caught on in the French literature. So if you look at Bertrand's book in 1888 or Poincaré's book in 1897, they refer to objectives and subjective probability. And in 1911, Otmar Sturzenegger, I think was German rather than Austrian, wrote a history where he says the history of probability theory is a constant battle between the two viewpoints, which we shall call briefly the subjective and the objective, although the meaning of these terms is already somewhat historically correct. So this important terminology, I think, really can be credited to Carnap. And I'll close this section with my final favorite quotation along these lines is Jacob Burckhardt's famous The Civilization of the Renaissance in Italy. And Burckhardt says that in the Middle Ages, both sides of human consciousness, that which was turned within as that which was turned without, lay dreaming or half awake beneath a common veil. In Italy, this veil first melted into air. An objective treatment and consideration of the state and of all the things of this world became possible. The subjective side, at the same time, asserted itself with corresponding emphasis. Man became a spiritual individual and recognized himself as such. So we can see this use of subjective and object. Whereas if you look in the OED, you'll see that going back to medieval philosophy, the terms were actually used for reasons I won't go into in an opposite way. Right, what was in the Middle Ages, subjective was what we call objective, and objective is what we call subjective. That's a story unto itself. Okay, so now on to a somewhat more technical aspect of the talk. There's an early Carnap and a later Carnap. I'm going to cast things in terms of what I'll call the later Carnap. So his setup is you have a sequence of outcomes, x1 through xn, or maybe infinite, and they take one of t values, which we call them C1 through CT. So C might be class, category, case, color, whatever, but we have t possibilities. And so if you give me a sequence of outcomes, I have n outcomes, each of which is being one of these things. A function, you're given a function on the t to the n sequences, right? You have t possibilities for the first, t for the second, t to the n in total. And the function p has the following properties. First of all, it satisfies the standard axioms of probability. It's exchangeable, at least as the first pass. And then you have his continuum. So this is where he stood basically, roughly speaking, in 1952. And this sparked a lot of discussion and interest in the subject. And but before getting into that in just a minute, it's now 70 years later, but quite apart from the technical issues that arose at the time, it seems to me that you can say Carnap's importance is he largely shaped the way current philosophy views the nature and role of probability. In particular, its widespread acceptance in philosophy of the Bayesian paradigm. Right. Okay, so I keep on talking about the shift. The Carnap and Jeffrey. So remember, there was this 2-volume. This was supposed to be, at some point, remember, Carnap gave up this project on writing one book after another, and he really thought of it as a research program, and there would be research reports issued from time to time. And the first set of reports was issued in this 1971 book that came out a year after Carnap died, co-edited by Jeffrey. But they have a very nice description of what happened. He said in Carnap's shift, says, furthermore, the technical apparatus elaborated in the logical foundations of probability no longer seems satisfactory. Okay, so final Carnap is saying, yes, I started out in this very and you still find people who like to work in that form, but Carnap himself had moved on beyond that. Why? Well, first of all, he started using mathematical tools like De Finet's representation theorem. So he wanted to do things more mathematically, which had not figured in his earlier work. Okay, and partly because of, and I think this is very important, a desire to formulate inductive logic in terms that come to be standard in mathematical probability theory and theoretical statistics. So Carnap came to recognize that, unfortunately, by having this, although it was a mode of approach that was very comfortable to him as a logician, from the point of view of communicating to the broader community of mathematicians and statisticians who might be, or even scientists who might be interested in this, really he had to shift and put things in a more mathematical way, where probabilities are attributed to events or propositions, which are construed as sets of entities, which you can think of as models. Okay, so the more modern way. Okay, so I'm going to give 3 studies now of how this is the right way for us to think about things as well. And the argument in each case is going to be that things that people debated about became much clearer when you think about this. So in 1950, and actually, in 1950 and actually earlier, that's in the book, and so this is a quotation from the book, he announces this principle that in the application of inductive logic to a given knowledge situation, the total evidence available must be taken as a basis for determining the degree of confirmation, which is how he referred to probability. When he says degree of confirmation today, it's really conditional probability. Probability, if you like, the probability of hypothesis given evidence, but more generally, it's just conditional probability. Now, in A.J. Ayer wrote an article in 1957, and he asked, so the great unsolved question of philosophy is, why is there something rather than nothing? Well, but here it's why are you better, as Brian Skirm said, why are you better knowing something than nothing? And so the point is, Carnap has this sort of consistency, especially when you start to look at it in De Fineti terms. You have this consistency theory, right? And so you could look on the probability of the hypothesis given E, or by conditioning, you could add it as the probability given H and give H given E and something else called F. And basically Ayer was saying, well, okay, you can look at condition on E and you can condition on E given F. Carnap tells us how to do this, but why are we better off in the second case than the first? And this sparked a spirited debate. And then, although there were predecessors, I.J. Good, Jack Good gave a persuasive answer to Ayer's question in 1967. So here's Good's framework. And I'll go through this very quickly, but you can look up his 1967 paper. It's short and very loosely written, but the idea is we have hypotheses, H1 through HR. We have acts, so those are the states of nature. We have acts, A1 through AS. And then in the Savage framework, you have a utility, UIJ. The utility of performing act AJ, given that state of nature AI, is the one that's actually true. The expected utility of AJ given HI. Now let's let PI be the prior probability. So think of E, by the way, as being, maybe I should have written I, but it's the prior evidence. Okay, so it's, so this is the prior probability of HI given your initial information. Okay, prior probability of HI given background E. And then the expected utility is you just average the UIJs that depend on I, the hypothesis HI, you average those by the probability that in fact HI occurs. And that gives you the overall expected utility. And then the principle of rationality is you choose that act which maximizes the expected utility. So here is the expected utility, and J star is that act which maximizes these guys. Okay. So here's the expected utility averaging over states of nature I. You take the find the maximum one depending on the act J, and then call that J star, and that's the act you choose. And I'll call this quantity B. So this is your expected utility B for before. Now suppose you have a free observation, and that'll be important in a moment, but suppose you, for free, you get to observe O, and it impacts the probability of the HIs. Your judgment regarding the different states of nature changes. Well, when you have this observation, you can have different possible outcomes, call them E1 through ET. And so there is now typically given the state of nature, you can sort of say everything. So in particular, in this framework, given the state of nature, you know there's a probability that each of these, that each of the possible outcomes occur. Okay, remember you observe O, and if HI is the one that obtains, that tells you the probability of seeing each of the E's. Now, given this, you can, by the standard Bayes theorem approach, you can calculate the prior probability of HI, given not just the background information, but also the new observation. Okay, so these E's give us posterior probabilities for the HI, and then you can just calculate the posterior expected utility for an act. Okay, and then what's the best act to perform? It's the one which has the best posterior utility. We call that A. So it's just straightforward exercise in math. I won't go you through the derivation, but I mean, you can just verify the steps. Okay. I mean, this is the posterior probability. This thing in parentheses is the posterior probability of the particular act J, and then you use that to average over those, and that gives you the best thing posterior, and call that A. I don't know that I said that quite right, but I'm just saying it's sort of clear what I'm saying, which is that you use the E's, the observation of the E's to change the probability for H, and then you just calculate the posterior expected utility, maximize that, and call that guy I, A, for after. Okay, and it's just a very straightforward calculation, just basis theorem. Okay, so, and this just reminds you what those things are. So here's a theorem. There's no philosophy here, it's just math, that A is bigger than or equal to B. So your after posterior expected utility is at least greater than or equal to the prior. And when do you have equality holds? Well, there's some J independent of K, which is the outcome of the experiment, that maximizes HA. So if there's a J such that this doesn't depend on K, it's saying you didn't learn anything useful, right? And so, yeah, if you're in this situation where there's a J which maximizes for every K, you haven't learned anything, so you certainly don't expect the posterior utility to increase. In fact, it's going to stay the same. But otherwise, when that's not the case, in other words, the utility for AJ depends on which one, the maximizer depends on which one you observe, then you actually have strict inequality. And so why is this, what's the proof of this theorem? Well, it's just if you just take a real function, it's a special case of a math lemma. If you have this function f of jk, you just have to prove this with this condition dominating rho corresponds to this condition for when you have equality up here, okay? Now, there are some assumptions to this. There's the Savage framework for rational decision-making. The effect of new information is via Bayesian conditioning. There's no cost for making an observation or using its information. Now, this last one is important because obviously if there is some uniform cost, then, so if there's cost, then it can change things. And so, for example, suppose there's a uniform cost C, both for observing and then making use of the observation. Well, if this is the increase in utility, it better be bigger than the cost for getting the observation and using it, because otherwise you'd be worse off. But precisely when A minus B is so large as to exceed C, then you're still better off. Now, what was interesting was Jack Good was well aware of this last issue because he worked at Bletchley Park. He was touring statistical assistant for the first year he was there. So because of his wartime work at Bletchley Park, and one of the things they did was they computed an expected weight of evidence. So if you looked at the likelihood ratio of the event relative to two hypotheses, and then took the log, so instead of being multiplicative, things were additive, then this is what was called the weighted evidence. And so the point was at Bletchley Park, when you were deciding whether or not you were going to try to attack some message, you had certain kinds of information you could draw upon, which would tell you ahead of time whether or not you were likely to break it in a reasonable amount of time. And, you know, there was a huge difference, you know, if you had an enable enigma message, there was a huge difference between being able to break it in 1 day versus 1 week. You know, 1 day was actionable intelligence, 1 week it probably was useless. So they were in a very practical decision-making kind of framework. So this kind of consideration was important. And so, yeah, but the point is, if there is a cost of making the observation and using it, then in general, there's no one right answer, right? It depends. But so the point of this is it though identifies circumstances on which there is a value of evidence. Now, the Savage framework, well, you know, if you have another framework, fine, step forward, and then you have another theorem you could try to prove instead, right? That's not a negative, it's just he's taking a framework, you're free to have another. What about the effect of new information? I think I'll skim pretty much through this slide here, but some of you may know that Dick Jeffrey, who was a philosopher at Princeton for many years, had this form of belief change where you went from P to P star, and it wasn't Bayesian conditioning. It's just that there was some partition of possibilities, partition meaning they were disjoint and exhaustive. And what happened was your probabilities on the H's changed, but conditional on the H's, the probabilities were otherwise unchanged. So this was a generalization of Bayesian conditioning. So it's a generalization because one thing you could do is you could just give one of these probability 1. But in general, Jeffrey's saying, suppose it's just the case that you shift the probabilities in some way. That was Jeffrey conditioning. And you can give people have given a value of argument, a value of knowledge argument in this case, and you can even update, generalize things to the idea of what's called a martingale. So Brian Skirms in his book on deliberation and Simon Hudiger have both done interesting work in this area. Okay, but you see the bottom line to me though is if you look at Good's argument, there's nothing actually, this isn't really rocket science. Now, if you knew Good, it was a very natural way to think, for him to think. I once met him at a conference and I mentioned a paradox that was just going the rounds at that point. And he was interested in it, he hadn't heard about it before. And he started thinking out loud. And he was very quickly putting this into some Bayesian framework where you understood exactly what was going on. So this is the way he thought. He was very Bayesian. And so this is, not rocket scientists, right? You're just saying that, fine, you want to talk about value, so you have to talk about utility. You want to say, what's the value of information? Well, obviously, it's going to be how it affects the states of nature, okay? And then you want to see, are you better off before or after? So you just have two expressions, the prior utility, maximum utility, and the posterior maximum utility, and you just ask a question, and then it's just a math theorem. So my point, and he has this puckish comment at the end, that there had been some discussion where you had 17, as he says, noteworthy philosophers who were arguing about this. And he said, I thought it was useful to publish this article because you had these 17 different guys arguing about it, and yet there's a very simple answer. And so that's part of this thesis, is that if you think about things in the right probabilistic framework, well, some paradoxes remain complicated, but in many cases, the mystery evaporates. So let me give another example, case study 2, the principle of instantial relevance, and I'll speed up a little bit. But suppose you have XK or indicators. So this, again, this is things people argued about it, but the bottom line is really simple. So let's XK be indicators, 0 and 1. Something did or didn't happen. And so what is instantial relevance? It's saying, suppose I observe something, does it make it more likely that such a type will be observed in the future, right? Well, if you write it down in terms of indicator variables, it's saying that suppose at stage I observed that something occurred. What will that do to my expectation at stage J? And the answer is if it occurred at I, then you'd like to say it's more likely, or at least as likely, as what it was without that information. So that's instantial relevance, okay? Observing something ups the likelihood of seeing the same thing happen again. Well, one starting model for inductive inference, so we're going from the axioms to another stage, which is models for inductive inference, and one important starting model is exchangeability. And exchangeability simply says that if you have a permutation of the integers, then observing, so E1 through En are possible outcomes. So X is just denoting the random experiment. E1 is the actual outcome. And exchangeability just says that observing a sequence has the same probability as observing the same sequence of things, but in some scrambled order. Whoops, sorry. Okay, so for example, in coin tossing, what's the chance of getting K heads and N tosses of a coin in some specific order, like HHT, HTTT? And the answer is, in general, whatever any specific order, if you have K heads and N minus K tails, they all have the same probability, namely P to the K heads, 1 minus P tails, right? And that's just because if you had K heads, you'll have K factors of P somewhere. And if you have N minus K tails, you'll have N minus K factors of 1 minus P. And the order, and because multiplication is commutative, the probabilities are the same. So that's what exchangeability is. But the point is, in exchangeable outcomes, you don't expect necessarily to have instantial relevance. So suppose you have an urn with 3 reds and 2 blacks, and X indicates if you have red or not. Well, what's the chance that I get a red on the first? Well, it's 3/5, right? Because you have a total of 5 balls in total, and 3 of them are red. So what's the chance of getting a red on the first? It's 3/5. Well, what's the chance of getting a red on the second, giving you red on the first? Well, if you have a red on the first, you've pulled the red out. Now you're down to 2 reds and 2 blacks. So the chance of another red is 1/2, which is less than 3/5. So when you're sampling without replacement from the urn, the probability decreases. But this assignment is also exchangeable. So for example, if you do 2 reds and a black, or red, black, red, or black, red, red, you can see in all 3 cases, although the factors jumble around, the bottom line is still 1/5. So exchangeability does not force instantial relevance on you. So how do we understand this? So there's something called the De-Finetti representation theorem. So let's just generalize what we were talking about. So let U, R, N, little n, we're going to have an urn with R red balls and n balls in total. And suppose we draw a sample of little n out of them. Okay, so that's what we were talking about before. Then it's easy to see that, just like in this concrete example, it's easy to see that in general, when you're drawing red and black balls out of an urn, and you draw, you have a total of n, but you draw just the first little n of them, it's easy to see that this guy is exchangeable. But it's also easy to see, and I mean easy to see like a two-line argument, just write it down, that if you take a mixture of these things where you mix over the possible compositions, are there 0 reds, 1 red, 2 reds through n reds, if you take a mixture of these exchangeable probabilities, it's still exchangeable. Very easy, just write it down. Okay, so, and that just reflects that in general, a mixture of exchangeable sequences is exchangeable. But there's a finite representation theorem, which is not as well known as this infinite cousin, but any exchangeable, finite exchangeable probability on such finite sequences is in fact of this form. The way you understand finite exchangeability is you pick an urn of a given composition with a certain probability, and then you pull out sampling without replacement from it. The infinite de Finetti representation is the twist on this. An infinite sequence is said to be infinitely exchangeable if you look at any finite segment of it and it's exchangeable in the previous sense. So infinite exchangeable just means you're part of a sequence that can be prolonged. In that case, the representation, right? So this is the one time I'll have an integral, but it's just basically you take the binomial probabilities for a success of p, and then you just take mixed. Now, instead of having a discrete mixture here, you just have an infinite mixture here. You just have a mu on this unit interval. Okay. Now, in the past, there was a small cottage industry devoted to investigating when does the principle of instantial relevance hold or not hold. And in particular, if observations can be bedded into an infinitely exchangeable sequence, you do have instantial relevance. Now, after the power of the de Finetti representation theorem was appreciated, and remember that quotation from the Carnap and Jeffrey 1971 volume, that was one of the reasons Carnap switched was to this math framework, was that he started using the representation theorem. And very simple proofs of this were discovered. So for example, in the Carnap and Jeffrey volume, chapter 5 is by Chaim Geifman. And then there's a chapter 4 by Humberg, which does the same thing, but in much more cleanly and elegantly after Geifman. But my point here is, well, you might say, gee, but the representation theorem says, really impressive math fact. Well, actually, it's much simpler. Because suppose you give me an exchangeable sequence, and in general, it doesn't even have to be zeros or one now. It could be anything in which you have this invariance under permutation. And you have this correlation coefficient of xi and xj, then it's easy to show that if you have an exchangeable sequence of length n, the correlation among a pair of observations is greater than or equal to -1 over n minus 1. Very simple. And the answer, why? Because you just take 0, and if you look at the sum of these guys, there's a formula, a general formula for the variance of the sum. And in the case of exchangeability, where any pair has the same distribution, so there's a common variance sigma squared, you can just show that this variance of the sum, which is always non-negative, is just n sigma squared plus this term here involving n rho and sigma. And if you rearrange it, you just get this. So this thing is trivial to derive. You derive it from this formula that you learned in your first course in calculus level probability. And now if you take the limit as n goes to infinity, this guy goes to 0. So if you have an infinitely exchangeable sequence, the correlation is necessarily non-negative, okay? And in the special case of indicators, the correlation is just that relevance quotient. Well, it's the ratio of one over the other. So showing that one is greater than the other is the same, as saying the ratio is greater than 1. Now it's greater than or equal to, but if you're equal to 0, that would correspond to being independent and for indicators. And if you're positive, it's positive instantial relevance. So here too is something where people are arguing a lot about this and coming up with complicated analyses. But actually, when you look at it in the right way, it's very simple. It's just about time to stop. Let me just skim quickly through. There's something called universal generalizations. And so in Carnap's continuum, so I can talk about this more in the questions if people are interested, but this is what Carnap's continuum of inductive methods is. You know, if you observe outcomes and you say, what's the probability of seeing something of a given type? Here's the formula. And it turns out that you can show that if a universal generalization is something of the form like if all ravens so far are black, then every raven is black, right? And what you can see in Carnap's system is that can't happen. That no matter how big an initial segment you watch, the more and more ravens you look at in the future, the probability that they're all black will decrease to 0. So this was seen as a defect in Carnap's system. Eventually, Hintke and Ninuoto came up with an interesting extension of Carnap's system that got rid of this defect. But at some point, I wrote a short paper saying that all you have to do is the key thing that was driving the analysis is the so-called sufficientness postulate, that the probability of seeing something given everything up to then is just a function of two things. What was in that particular category, right? And the total number. But you don't care about everything else here. If you want to know what's the chance that the I thing occurs, just tell me how many I things I've already seen and what the sample size was. But that rules out this possibility of universal generalizations. And the simple fix, so I wrote a paper at some point showing how it was just possible in like 2 pages to come up with a little argument to show that if you take into account how many species have been, how many types have been occurred, so that, you know, so this now you stick in how many things have been observed. As long as the number of things was observed as 1, you're in the universal generalization case. And you can, this goes away. If you have a universal generalization, there's some chance that it'll always be this way. And then there's a Johnson-Carnap piece. But although there's this complicated Hintke-Ninuoto theory, which is very beautiful and impressive, the point of this short paper I wrote was it's actually not hard mathematics if all you're interested in is this special case. And I just give a little extract from my paper. And so the point is, as long as everything is of one type, this is the probability it'll always be of that type. And then 1 minus that is this Johnson-Carnap piece. Okay, and oh, and I actually have one more slide, so I've gone a little bit over, I apologize. But this is just to reinforce that Carnap really evolved over time. So I think if you want to understand and interpret Carnap, you really have to take that into account. So in the posthumous, so in this Jeffrey, the 2nd volume, that was edited by Dick Jeffrey, this part 2 of Carnap's basic system appears, and in it he makes this important point that he says, I don't think there's a controversy between the objectivist point of view and the subjectivist or personalist point of view. But remember, he's using subjective, objective, not in Cournot's idea of physical versus personal probability, but he's using it in terms of its degree of belief, but it is a logically compelled degree of belief, or is a degree of belief in the sense of a judgment on someone's part. And he says, I don't think there's really a conflict between those two. They both have a legitimate place, namely the construction of a set of rules for determining the probability values. At each step in the construction, a choice is to be made. The choice is not completely free, but it's restricted by certain boundaries. And so basically the difference is there's merely a difference in attitude or emphasis between the subjectivist emphasis of choice and the objectivist emphasis on limitation. Right, so I'm trying to come up with this. Now, I think the English philosopher Johnson had a better way of putting it, which is what we're doing is coming up with rules, and then in any given situation, we have to see whether or not those rules are applicable. But you can already see that there's been a substantial step back by Carnap from this objective, you know, from the purely objective. At the end of his life, he was not, I'd say, an objective probabilist in the sense that there was always had to be a right answer. With that, I will cede the floor and say thank you.
Thanks so much, Professor Zabell. So now we can move on to the Q&A time, and let me also